Hi everyone, my name is Charlie Como, and this is my video lab report for our first lab. Our goal here is to experimentally determine the amount of charge on a piece of tape by measuring the distance at which one tape makes the other float from its electric force. First, we will determine its sign through its reaction with a negatively charged object, then use two fundamental electrical physics principles, electric charge and electric force, to mathematically derive the magnitude of the charge, and finally use Avogadro's number to find the percentage of the tape's atoms that are missing electrons and are contributing to the tape's overall charge. For some background info, this is the electric force equation, with its constants and characteristics shown on the screen. Note E is a fundamental physics constant. We are going to make the following simplifying assumptions, which are assuming that each U-tape has a single point charge located at the center of the tape, and pictured is the tape I will be using for this experiment. Putting all this together, this is the derivation that allows us to find our charge. When the bottom tape just begins to make the top tape move, the top tape reaches a state of static equilibrium where the net force is zero, meaning that the magnitude of the electric and the gravitational force on the top tape are equal. After applying that both tape charges are equal, we derive the equation on the top right for the charge of our tape. We can then multiply our calculated charges to find the number of electrons absent in our tape. Here are some videos of a confused physicist in action. Now here are two interacting U-tapes. I predicted that the two tapes will repel each other because they're the same charge, and the video supported my beliefs with the split bottoms. Here are some analysis of questions about the tape charge with respect to a negatively charged plastic pen. Note, if the U-tape is positively charged, it will be attracted to the pen. If it is negatively charged, it will be repelled. And if it is neutral, it would still be attracted because the negatively charged pen would attract the U-tape's proton and make its electrons move. Here's a charge check, which came back positive. It's ridiculous. Here's a gravity check of our U-tapes. I noticed that the top tape began moving when the bottom tape was 2 centimeters away. Note the length and width of my tapes were 20 and 5 centimeters respectively, which led to a corresponding mass of 0.2 grams. Plugging in all these experimentally measured numbers into our previous derivation yields a calculated charge of 9.33 times 10 to the negative 9th coulombs and 5.62 times 10 to the 15th electrons for our tape. Assuming that an atom's area is 10 to the power of negative 20 meters and that the tape atoms are packed side by side perfectly like a grid, we find that 0.562% of our tape's atoms gave up their electrons. Here are some further analysis questions. Now, if the protons and electrons switch their charge, the only observation that would change is the sign of the individual charge of each tape. Also, the reason behind the importance of minimal charge tape handling is because any direct contact with another object provides a path for either the tape's electrons to flow away or the object's electrons to flow into the tape, which changes the overall charge of the tapes and erroneously distorts our calculations. And here is all of our work coded up in Python as a computational model. Note, we use the same two aforementioned assumptions in creating our model, and this is what it looks like. Green arrows symbolize electric force, and the white ones symbolize the gravitational force. Note our Python charge equals our calculated charge. The gravitational force points down on each tape, and the electric force points in opposite directions since each tape's charge has the same charge. The magnitude of each object's electric and gravitational force are equal. The top tape is in static equilibrium, and the bottom tape has both the gravitational and electric forces pointing down. In conclusion, we successfully used fundamental physics principles to find the charge of each tape, which was 9.33 times 10 to the negative 9th coulombs. If I were to do this again, one improvement could be to have more professional equipment to make more stable measurements instead of using my homemade ragtag gang of objects. Overall, this experiment was a success.